The overall goal of this procedure is to describe a method to express fresh pore solution from a plastic cementitious-based system using a stainless steel pressurized nitrogen gas filter, and to measure the pore solution chemical composition using an energy dispersive X-ray fluorescence benchtop spectrometer. The chemical or ionic composition measured by the XRF can be used to calculate the electrical resistivity of the pore solution, which can then be used in conjunction with the electrical resistivity of concrete to determine the formation factor. Since XRF is a commonly used device in the cement industry, this method could potentially enable cement manufacturers to use a tool already at their disposal to provide more information about the cementitious pore solution, such as the ionic composition and resistivity, for numerous applications and at a lower cost and testing time than conventional methods. Essentially, this method could extend the applications for the use of an XRF for a variety of cement and concrete studies. To begin this procedure, check that the individual components of the pore solution extractor are clean and dry. Then, assemble the pore solution extractor according to the manufacturer's instructions. Check that there are no visible deformities in the cellulose filter. Next, add the fresh paste into the main chamber. Make sure to leave at least 1 centimeter from the top free. Then, connect the pore solution extractor to the nitrogen source and seal the main chamber. Use a clean canister to collect the pore solution. Open the valve of the nitrogen tank. Use the pressure gauge to regulate the pressure to 200 kilopascals. Maintain constant pressure for a period of 5 minutes. Transfer the pore solution to a 5 milliliter syringe. Make sure to eject all air bubbles in the syringe. Seal the syringe with a needle cap. Test immediately or store inside a 5°C chamber until testing. Assemble the solution testing containers. Make sure that the plastic cylinders are clean and dry. Place the polypropylene film on top of the larger cylinder. Insert the smaller cylinder on top of the larger cylinder. Push down on the smaller cylinder, pressing the film in between. Ensure that the film is smooth and has no tears or deformations. Inject at least 2 grams of the pore solution sample in the assembled testing container. Seal the container with the lid. Leave the container with the solution on a paper towel for 2 minutes. Check that the film has no leak. Place the sample inside the XRF sample holder and close the XRF. Analyze the sample for ionic composition. The main ionic species present in pore solution needed to calculate the electrical resistivity of pore solution are sodium, potassium, calcium, sulfate, and hydroxide. The results from the XRF analysis will show the concentration of sodium, potassium, calcium, and sulfide ions. A series of calculations are then completed to obtain the concentration of the sulfate and hydroxide ions, and the electrical resistivity of the pore solution. First, use stoichiometry to calculate the concentration of the sulfate ions based on the concentration of the sulfide ions detected by the XRF. Then, use a charge balance to calculate the concentration of hydroxides in the pore solution. After obtaining all the ionic concentrations of the 5 ionic species considered, convert the ionic concentrations from parts per million to mole per liter, assuming a density of 1,000 gram per liter. And finally, Use the model developed by Snyder and others to calculate the electrical resistivity of the pore solution. The results from the previous calculations should yield the ionic concentrations of the main 5 ions in cementitious pore solution and the calculated electrical resistivity of the pore solution. After watching this video, you should have a good understanding of how to express fresh pore solution from a plastic paste sample using a pressurized nitrogen gas filter, and to measure the pore solution chemical composition using an energy dispersive X-ray fluorescence benchtop spectrometer. From the measured values of the XRF, you should be able to obtain the ionic concentrations of the main ionic species present in pore solution, and to calculate the electrical resistivity of pore solution. This information can be ultimately used in conjunction with the electrical resistivity of concrete to calculate the formation factor, and for other concrete durability applications and concrete studies. If performed properly and safely, this procedure should take no longer than 20 minutes from start to finish.